All right, in this video, we're going to talk about section 4.8 that deals with Newton's method. And in this section, we'll look at how we can use Newton's method to approximate roots and reciprocals. Okay, so what this method is, it's just a way of finding the zeros or the roots of a function. Okay, and if you recall, the roots of a function are going to be the values of x that satisfy the equation f of x is equal to 0. In other words, we're going to be looking for the x-intercepts of the graph of the function f of x. All right, so what we're going to do here first, I'm going to show you how Newton's method is derived. Okay, and we're going to derive this geometrically, where we're assuming that r is a function, r is a root of the function f of x that we wish to approximate. This means that f of r will have to be equal to 0. We also assume that the function is differentiable on some interval containing r. Excuse me. Let's say x of 0 is an initial approximation to r that is generally obtained by some preliminary analysis. And the best approximation to r is often obtained by carrying out these two steps. One, we want the line tangent to the curve y equal f of x at the point x of 0, comma, f sub 0 is drawn. And then at the point x1, 0, at which the tangent line intersects the x-axis is found, and x1 becomes the new approximation to r. So let me explain what that means here. If I was to illustrate this, here we got the graph of y equal f of x, okay? And we got some point x of 0, all right? So, excuse me. All right, so here's x sub 0 right here. That's the point on the x-axis. The point that's corresponding to that would be, in this case, right here. Let's see, that's the point right here. So this point is the ordered pair x sub 0, f of x sub 0. Okay, that's the point. Now let's say I want to draw a tangent line to this point that I just drew. So if I draw a tangent line, and of course a tangent line is just a line that touches the graph at that point. So this would be my tangent line here. Notice that this tangent line that I just drew crosses the x-axis at this point. And that point we're going to call x1. Since that's x0, this point here, where the tangent line crosses the x-axis, will be x1. Okay. And then that x1 would become the new approximation for r. Excuse me again. All right, and then next I draw another point where x1 is on the graph of y equal f of x. Let's say this right here. Now that point is going to be x sub 1, f of x sub 1. F of 1, f of x sub 1. And now I'm going to draw another tangent line at that point. And here I'm going to use a different color. So if I draw another tangent line like this, and that tangent line is going to cross the x-axis. So there's my tangent line there. That tangent line intersects the x-axis at this point, which I'm going to call x2. So now x2 would be my new approximation. And then I continue this process here by drawing the point on the graph where x of 2 is at. That will be here. And that point is going to be x2, f of x2. And then I draw a tangent line for that. Okay, so using another different color. In this case here. And as you can see here, that tangent line crosses the x-axis at this point here, which I'm going to call x3. Okay. And now let's see here at x3 is the point right here for x3. That ordered pair is x3, f of x3. Okay, and now I'm going to draw another tangent line at that point. All right, and that tangent line here that you see in orange crosses this x-axis at this point, which is going to be x4. The idea that I'm impressing upon is this. The more tangent lines you draw on this graph, the closer you're going to get to what R is equal to, okay? That's the idea of Newton's method, okay? And this is more illustrated on the next page of this handout, as you can see, okay? So here, if we were to continue in that fashion, we obtain a sequence of approximations x1, x2, and x3, and so on, that ideally get closer and closer, or we use the word converge to the root R. So here in this case here, we're converging, we're trying to get closer and closer to R as we continue to draw more tangent lines in this case. Now, what's left is just finding a formula that captures the process that I just described here. All right, so what we're going to use here is that point slope form of a linear equation, if you recall from college algebra, and I will write that down. In this case, here it's going to be y minus y1, and that's equal to the slope m times x minus x1. And here we're dealing with a ordered pair. Let's call this x of n and f of x of n. Okay. Because I've been labeling the points as x of n and then ordered pair that's on that graph of y equal f of x was x of n, f of x of n. Okay. So now, if we were to use the point slope form here, this will be, I'm going to call this x1, and that's y1, of course. So now, substituting in the point slope form is going to be this, y minus y1, in this case is f of x of n, that's equal to m times the quantity x minus x1 is going to be x of n. All right, now for m, if you recall, that's the slope of the tangent line. And the notation that we use for the slope of the tangent line is always going to be f prime of x of n, f prime of x of n. If this function is y is equal to f of x n, the slope, the derivative of that would be f prime of x of n. That gives us the slope of the tangent line at that value, x of n. So let's replace that m. I'm going to bring down the y minus f of x of n replace the m with f prime of x sub n times the quantity x minus x sub n. This is the left parentheses here. Now, of course, when we're finding the root, we're trying to find out the value of x when y is equal to 0. Okay, of course, you're finding what they call the x-intercept. Anytime you find the x-intercept, you always substitute your y with 0. So this y will be replaced with 0. So this would be 0 minus the 0 minus f of x sub n, and that's equal to f prime of x sub n times x minus x sub n. And of course, 0 minus f of x sub n will be negative f of x sub n. And that's equal to f prime of x sub n times the quantity x minus x sub n. Now, what I want to do here is get x by itself. Here, I want to solve for x here. So the first thing I need to do here is get rid of the f prime of x sub n. That x minus x sub n is being multiplied by f prime of x sub n. So I need to divide both sides by f prime of x sub n. So in this case here, that f prime of x sub n divides out. That's gone. I'm left with x minus x sub n on the right side. And that's equal to negative f of x sub n divided by f prime of x sub n. And of course, to get x by itself, I'll move the minus x sub n over to the other side. So this x will be by itself. On the other side, it'll be x and then minus f of x sub n. And that's only divided by f prime of x sub n. Okay, so all I did was move x sub n over to the left-hand side. So this should be x sub n here, minus f of x sub n divided by f prime of x sub n. Okay. And let me go ahead and write the x on the left side. It'll be x is equal to x sub n minus f of x sub n divided by f prime of x sub n. All right, so that's how Newton's method is derived from this to get this formula. X is equal to that value, that expression, x sub n minus f of x sub n divided by f prime of x sub n. And only f of x sub n is divided by f prime of x sub n, not the whole thing. Okay. Now, if I want to call this x sub n plus 1, I would end up with this. And I'll write this out as x sub n plus 1. And that's equal to x sub n, which is the current approximation, minus f of x sub n divided by f prime of x sub n. And that's provided that f prime of x sub n is not equal to 0. So that x sub n plus 1 becomes your new approximation. Okay. Now on the next page is the procedure for Newton's method for approximating roots of f of x equal to 0. Number one, you're going to choose an initial approximation as close to the root as possible, and that initial approximation will be x sub 0. And in these examples I'm going to show you, you're going to be given x sub 0 to be equal to some value, so you won't have to worry about choosing an approximation. And now number two is this: for n equal to 0, 1, 2, and so on, x of n plus 1 will be equal to x of n minus f of x of n divided by f prime of x of n. And that, of course, provided that f prime of x of n does not give you a 0. And then number 3, you're going to end the calculations when a termination condition is met. And what I mean by that is if you go through this Newton's method for each iteration, and then that next iteration gives you the exact same value for x of n plus 1, you can end the calculation right there and say that this will be the 0, that value will be the 0 for that given function. Okay. And in the notation, it says here that Newton's method is an example of a repetitive loop calculation called an iteration. Now, the most efficient way to implement the method is with a calculator or computer. The method is also included in many software packages. So here we're going to use a table, and then I'm also going to show you how to use the graphing calculator, mainly the TI-84 Plus calculator, to come up with your iterations here. All right, let's start with example 1. Here we're going to write the formula for Newton's method and use the given initial approximation to compute the approximations x1 and x2. And here we got the function f of x is equal to x squared plus 4x minus 32. And our initial approximation, x of 0, is going to be equal to 6. So here we're given the initial approximation. So we're going to use that. We'll start with that to compute approximations just for x1 and x2. All right. So that means here, whatever I get in the first row will be the approximation for x1, the next row for x2. And we'll stop right there because they just want the initial approximations for just x of 1 and x of 2. Now, the n is that subscript for your x, which is 0. So I'm going to enter 0 here. X of n or x of 0, they give us 6 as the value for x of 0. So we enter the 6 there. Now for f of x of n, well, let's do this. I know what f of x is. That's x squared plus 4x minus 32. So that means f of x of n will be this. Just replace the x with x of n. So this will be x of n, and that's squared, plus 4 times the x is replaced with x of n minus 32. And notice right here, I also have f prime of x of n. I need to know what that first derivative is for this function here. So if f of x is equal to f of x is equal to x squared plus 4x minus 32, then f prime of x, if I take that derivative, the derivative of x squared will be 2x, plus the derivative of 4x will be 4. And the derivative of a constant is 0. So that's what f prime of x is. Now, f prime of x of n, we just replace the x with the x of n. So it'll be 2 times x of n plus 4. Now, what I'm going to do is go ahead and write the formula for Newton's method. Okay, so in this case here, that Newton's method is this: x sub n plus 1 is equal to x of n minus f of x of n divided by f prime of x of n. All right, so x of n, we bring that over, minus f prime of x of n, that's this right here. I mean, f of x of n, I'm sorry, that's this up here. x sub n squared plus 4x sub n minus 32. So I'll go ahead and write that. X sub n squared plus 4 times x sub n minus 32. The whole thing is divided by f prime of x sub n, 2 times x sub n plus 4. All right, now I'm going to tell you in the homework, they're going to ask for you to select the appropriate formula for Newton's method for this function. And this is going to be it. That's what they're going to ask for in the homework. Okay, now we're going to use a given initial approximation to compute the approximations of x1 and x2. And notice that I do have this chart split up to this. You're going to evaluate f of x sub n, and then f prime of x sub n. Then f of x sub n divided by f prime of x sub n would be this. You'll take this value here, whatever that is, and divide that by this value right here, and that will give you this. And then to come up with x sub n minus f of x sub n divided by f prime of x sub n, you'll take this number minus whatever this number is to get this. Okay, let me show you how this is worked out. For f of x sub n, x sub n is 6. So that means for each x here in f of x, I need to replace it with the 6. Okay, and if you want to, you can use the calculator to do this. Throw this out. All right, x is 6, so in f of x sub n, this right here, this will be 6 squared. Oops, 6 and then squared plus 4 times x sub n, that's 6, close parentheses, minus 32. Hit enter. That would give you 28. So that 28 goes in this box here. And then for this one, f prime of x sub n. Here, f prime of x sub n, that's the 2 times x sub n minus 4. And again, x sub n is 6. So I'm going to substitute this x sub n with this 6. So it'll be 2 times 6 plus 4. And that would give me 16. So that 16 will go here. Okay. Now, f of x sub 0 divided by f prime of x sub 0, that's this value divided by this value right here. F of x sub 0 divided by f prime of x sub 0, that's 28 divided by 16. So if I do 28 divided by 16, that would give me 1.75. So that 1.75 goes here. I took this number divided by this number to get that 1.75. And then finally, x of n minus f of x sub 0 divided by f prime of x sub n. In this case here, that's going to be the x of n right here, which is 6, minus this number right here, 1.75. So if I do 6 minus 1.75, that would give me 4.25. So x sub 1, in this case, is 4.25. Now that was the first iteration. Now to come up with the second iteration, this is what I'm going to do here. That n is going to be now 1. But this 4.25 that I have here, that's going to become the new approximation here. So this 4.25 would go right here as x of n. That would be the new approximation. So 4.25 goes there. And now we're going to evaluate f of x of n. We're going to use this, substitute x of n with 4.25 this time. So using the calculator, I'm going to put 4.25 in parentheses and then square it, plus 4 parentheses 4.25 close parentheses minus 32. And you can see I come up with 3.0625. So that goes in the box for f of x sub n. And now for f prime of x sub n, which is of course 2x sub n plus 4, I'm going to replace that x sub n with this 4.25. So now I'm going to have 2 times 4.25 plus 4. And here I end up with 12.5. So f of x sub n here will be 12.5. And then I'm going to take f of x sub n divided by f prime of x sub n to get this value. That's this number divided by this number. So if I do 3.0625 and divide that by 12.5, I end up with 0.245. So that means 0.245 is what f of x sub n divided by f prime of x sub n will be. And now to come up with this number in the last column, that's x sub n, which is this number, minus the quotient of f of x sub n and f prime of x sub n, which is this number right here. So I need to do 4.25 minus 0.245. That will end up being 4.005. All right, so this is what x sub 2 would be. That's the second iteration, which is 4.005. Okay, and that's what this problem, it asks for. It just wants the approximations for x1 and x2, and these are it. x1 was 4.25, and then x2 was 4.005. But if you were to carry that out, you will have to do that until you get your final number in that column the same as the one in the same. Okay, and we'll look at a couple of examples of that, in a few minutes. All right, here's another example. Let's say we got f of x is equal to 3 e to the negative x minus 14x. And our initial approximation is x sub 0 is equal to the natural log of 5. And we want to write the formula for Newton's method and use the given initial approximation to compute the approximations x1 and x2. So we want to find out what x1 is going to be, which is going to be this last number in this first row. And the last number in the second row will be x sub 2. All right, let's first find our formula for Newton's method. All right, in this case, I need to write this in the form of f of x sub n. F of x sub n. So all I do there is just substitute every x in f of x with x sub n. So this will be 3 e to the negative x sub n minus 14. And that x will be replaced with x sub n. Now I also need to find the derivative of that function. So if f of x is equal to f of x equal to 3e to the negative x minus 14x, then that means that f prime of x, if I take that derivative, all right, let's be careful here. If I bring over the 3 and then take the derivative of e to the negative x, that would be e to the negative x. But I also have to apply the chain rule by taking the derivative of negative x, which is, of course, -1. So that means a negative has to go in front of the 3e to the negative x. So I have -3 to the -3e to the negative x, and then minus the derivative of 14x will be 14. And then for f prime of x of n, just replace the x with x of n. So it'd be -3 e to the negative x of n minus 14. Okay. And now my x of n plus 1, of course, is always going to be x of n minus f of x of n divided by f prime of x of n. All right, so by doing the direct substitution here, bring over the x of n, that'd be minus f of x of n is that 3e to the negative x of n minus 14 x of n. I'm going to put x of n in parentheses. That's divided by my f prime of x of n, which was -3e to the negative x of n minus 14. Okay, and again, in the homework, that's what they're going to be looking for is the formula for Newton's method, which will be this right here. Now let's use that to approximate and the given approximation to compute the approximations for x1 and x2. All right, so here you're given that x of 0 is ln of 5. So your n starts off as 0. X of 0 is ln of 5. And then to find f of x of n, well, your x of n is ln of 5, so every x of n, you're going to replace it with ln of 5. Now I'll show you how to do that on the calculator. All right, I'm going to clear this out. All right, let's do here. Type in the 3 and then second ln for your e, and then the negative key. Ln of 5, I just press the ln key and then 5, close parentheses, and then use my right arrow key to get out of it, minus 14, and then in parentheses, x of n is that ln of 5. So I press ln 5, close parentheses for the 5, and then close parentheses for that left parentheses that we typed in, and then press enter. Let's say if I want to give this answer to 6 decimal places, this will be -21.932131. That's what f of x of n is. And now for f prime of x of n, in this case here, x is ln of 5, so we just replace each x with ln of 5. Anthony Wilkinson's office. Okay, how are you? Okay. Okay, I could look at it and see if I can add try to add extra points to it if at all possible. I think it is. I think it is chapters 8 through 9. Yeah. Yes, it should be open this coming Sunday. Yeah, if you want to go ahead and do it tonight, that's fine. I mean, and turn it in as soon as you can. That's fine. All right. Oh, I'm gonna create a video and I'm being interrupted.